Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everyone, and welcome. Welcome to another episode of Ask Us Anything About Electrochemistry. I am your host today. I'm Dr. Neil Spinner. I am an electrochemical engineer with Pine Research. We're an electrochemistry company in the United States, and we have been doing these sessions on live streaming primarily on YouTube for over a year now. I think this is episode 61, maybe, if I'm not mistaken. And these are forums for you as an electrochemistry researcher to do as the title suggests, which is ask us anything about electrochemistry. So working for an electrochemistry research, well, a company that makes research equipment for electrochemistry, my company makes these products. And when I was in graduate school and as a postdoc, I used these research products to do a lot of different electrochemistry research. And we've just observed over the years that we get lots of questions through different forums on the phone and through email, webinars, and various other media. And we realized that a good opportunity was to have a live stream where we can answer questions that folks have about electrochemistry and try to give a little more of an in-depth answer, draw some things, discuss them a little bit more in detail when the cases arise. So that's what this is for. If you're watching this video after the fact on our YouTube channel, thank you very much. And if you do have a question, you can join us at this time on Fridays at 1 p.m. Eastern US time when we go live as often as we can. My normal co-host Alex Paroff isn't with me today, as you can see, but one of us tries to do these each week, although in the summertime, as it is now, schedule tends to be a little more on and off. In any case, thank you for joining me if you are here. And to those who are watching after, again, if you have a question, you can either type it in the comments section of the video, or you can join in a future live stream and ask live by typing your question in the comments or in the chat box, I should say. Through our experience, we've noticed that there are a couple of different extremes of questions that tend to not be as helpful. And so the first is the very general, broad kinds of questions that are like, what is electrochemistry? What's the meaning of life? Very broad, overarching questions that are either hard to answer or at least hard to answer succinctly in a short amount of time in a forum like this. And so those may be not the best questions to ask. And then the other extreme would be something that's so specific, like what is the activation energy for the third electron transfer of an iron cobalt complex in alkaline media at 37 degrees Celsius. Some of these kinds of questions, of course, may be perfectly reasonable questions to ask or study, but unless I happened to do my research in graduate school on that exact topic, for instance, it's probably unlikely that I will know the answer, and it's not something that I'm going to be able to answer, without some literature study or anything like that. So basically, anything between very, very broad and very, very general is kind of the sweet spot that hopefully, if you have a question, you can ask something in that range. But other than that, we are happy to answer any questions. As this is, as I said in the beginning, this is the summertime, so people don't tend to be as around. I know a lot of people are on holiday and everything, so normally these live streams run for about 2 hours, depending on how many questions there are. If there aren't as many questions, then I won't likely go for 2 hours, but if there are lots of questions, I will try to answer them for as long as people have them, I suppose. And I see our good friend Chris is here. Good to see you, Chris. So Alex normally does all of these announcements, and I always feel like I'm missing something. But if I am, my apologies. I will just move on anyway. So there was one question that was I had answered on this event. I think I made it on YouTube maybe 2-3 days ago, and I do try to monitor the chat throughout the week leading up to now when I am, of course, live. And if, as a side note, if anybody is aware why YouTube tends to do this, it's like someone puts a question in the chat, and then after a day or two, it disappears. And I don't know why that is before it's live. So right now, if you're joining me and you ask a question, type it in, I'll see it and I'll answer it. And I can show it on the screen like this, where Chris says good morning, and you can see that he says good morning. But the question that was asked 2 days ago doesn't, it disappears for some reason. Anyway, this is a side note, and I just thought if anybody knows how Google, YouTube, Alphabet works programmatically, I would be curious to know. I don't really understand it, but fortunately, I do try to catalog the questions separately in this exact case because Ismail had asked a question, as I said a couple of days ago, and I wanted to make sure I didn't miss it. So that aside, the question was actually a relatively simple one, but he asked, is it okay to leave the Gamry 1010 potentiostat on for 5 days as to automate it for a 24-hour reading? And so I did answer as well. I typed an answer at that time, and as well, my typed answer has disappeared as of now. Again, I'm not sure why this happens, but it does apparently. And so the short answer is that I can't exactly give you specific information on Gamry's potentiostats or software, as I work for Pine Research. That's the, if you're watching this, I suppose that's the channel you're on. And so my company, Gamry's an excellent company, but it's not my company. So I don't know the specifics of their instruments. That being said, almost for sure, it should be fine. Almost any commercial potentiostat can run 24/7 constantly. Gamry included, my company Pine, our potentiostats can run continuously without any problems. That's pretty normal as well. You consider some common kinds of research that people will do in electrochemistry are like you might do cyclic voltammetry like 1,000 cycles or 10,000 cycles if you're trying to test the stability of a catalyst, let's say, or a battery test you might run for weeks or even months. And so equipment can run not just 24 hours, but 240 hours or very, very many. So my short answer, Ismail, is that most probably this should be no problem whatsoever for anybody running almost anything, provided that you are in a place where have a battery backup in case the power goes out. If there is a interruption, of course that's a separate issue, but the instruments themselves almost for sure shouldn't have any problem running continuously. Okay. Chris had some YouTube information. It's more often than not broken. You had to reload today to get the stream to show. That's very weird. Yeah, I don't know. I don't really have anything bad to say about YouTube's live streaming. I'm not trying to castigate or I don't know, cast any judgment on them. It's just the disappearing question thing has always been something odd to me because that's the purpose of a live stream, is to have a chat and then to catalog it. Like everything that's happening now, all of you folks who are typing into the chat, thank you very much. I'll get to these questions in just a moment. But these are all saved as well. So for example, if you're watching this later, you'll see the chat, all these chats on the right side of the screen usually. But not before it went live. And that's my point. So I just don't know if it's it might just be one of those kinds of oversight things that programmatically they haven't addressed yet. But in any case, I'll stop blathering on about YouTube and move on to these questions. So Anurag has a question, says that I've been working on microbial fuel cell in last year's master's degree. Could you explain more on this topic? It will be helpful for my paper. Okay, so I can talk about fuel cells more generally, and I will, let me see. I might not be able to speak super well on the specifics of microbial fuel cells, but I can at least talk about a fuel cell, and then, you know, if it extends, I suppose you would say, towards microbial fuel cells specifically, if you know what I mean, that might be helpful. I'll try to share. I have a animation that will show you how microbial fuel cell works, hopefully. Let's get this shared for you and hide this. So this is a proton exchange membrane fuel cell, or a PEM fuel cell. And so I have just a sort of an animation or description of how this specific device works. But again, as it relates to a microbial fuel cell, there is perhaps some analog, right? Structurally, a fuel cell consists usually of an anode, a cathode, and a membrane that separates them. So you see there's a membrane in between, this yellow or orange color, and then an anode and a cathode. Okay, the cathode is typically where the reduction occurs, the anode is typically where the oxidation occurs, and then they are connected through some external circuit, through something that produces or requires energy, electricity, right? With a and Chris has a good point too before I get going on this, but that you'd expect with a microbial fuel cell, there's a lot of special considerations for the electrolyte and the nutrient. I think that is the case. Anecdotally, all I can sort of tell you, I'm not trying to start a war here, but I studied some fuel cells, alkaline and PEM, when I was in graduate school. And so I know how they work a little bit. And my boss was not, shall we say, the biggest fan of microbial fuel cells as a subcategory. Now, there's some sort of funny reasons for that, and and compared to state-of-the-art platinum proton fuel cells, they're not as efficient or as powerful. The power and the specific energy you can get from a microbial fuel cell is not as great. That doesn't mean that it's not an important topic or doesn't deserve study, let's say, but in any case, it is used for wastewater or things of that nature. It can be quite useful. Again, for a PEM fuel cell, I'll just sort of talk about how this works. You feed hydrogen into one side. Basically, a fuel cell fundamentally operates with one reaction that's split into two, one at the anode, one at the cathode, right? And so with a PEM fuel cell, half of that reaction is at the anode, which is basically just ripping hydrogen into protons and electrons. Again, for a PEM fuel cell, the protons go through the membrane, which is usually something called naphion. The electrons go through the external circuit. That's what makes power electricity. That's what powers your device or your storage or whatever it is. At the cathode, you feed oxygen. And at the cathode, we have the oxygen reduction reaction, which produces water. And so you see that the electrons and the protons make their way to the other side, to the cathode, one of them through the membrane, one of them through the external circuit. They combine with the oxygen molecules and they make water. And so the overall reaction for this fuel cell is hydrogen plus oxygen plus some electrons. Basically just hydrogen plus oxygen makes water, right? The electrons are released by one and consumed by the other. So the overall reaction is one chemical reaction, right? Hydrogen plus oxygen gives you water with the correct stoichiometry. The thing about the fuel cell is that it splits them into two individual redox reactions, one oxidation, one reduction. And so without being more specific, right, as I said, with respect to microbial fuel cells, I don't 100% know what the half reactions or overall reaction is for a microbial fuel cell, because I don't know exactly first of all, what is the thing it's trying to produce? Now, again, I think that you have living, microbes, and a lot of times it's like aqueous water, sometimes wastewater. So there's a lot of nutrients, there's a lot of minerals and things in the either side or both sides, and so it's quite a bit more complicated, and it's a more complex situation. And so there might be other side reactions, and I know that with microbial fuel cells as well, you can get a lot of fouling because it's biological material. And so when you have biological material, very often you get films, and it can coat the catalysts in the membrane. It can plug up stuff. These are some practical concerns that can happen. You have to sort of refresh them from time to time. But other than that, I don't know that I can give you more specifics about microbial fuel cells. Other than that, what I showed you is roughly how a fuel cell works. Replace the anode and the cathode, reactions, or other parts with whatever are specific to your microbial fuel cell. And I suppose that's roughly how they work, or whatever I can tell you about them. Chris says, on a related tangent, thoughts on oxygen producing polymetallic nodules in the deep ocean? I have not seen this, actually. It sounds really fascinating. Oxygen producing polymetallic nodules in the deep ocean. Anything that happens in the deep ocean is immediately fascinating, because it's like what it says, 3/4 of our planet is water, and it's like, I feel like wherever you look you find a different number, but it's like 90% of the ocean's unexplored, or we don't know anything about it. It's insane. It's like, sometimes it feels like it's 2024. How do we not know everything about everything? But somehow we don't know almost anything about the ocean, especially in the deep part of the ocean, because the pressure is so great. There's no light. 0.95 volts. That's it. That's incredible. Like 1 volt making oxygen. That's incredible. Yeah, I mean, there's so much. It feels like there's so much untapped potential within the ocean, and just, I mean, it's such a vast, obviously semi-infinite reservoir. So that's cool. I'll have to look at that later. I won't look into it now, but that sounds fascinating. Okay, let's see here. Noreen has a question: how the interface stability is enhanced in solid state lithium sulfur batteries to affect overall conductivity of the battery. So I guess you're referring to the solid electrolyte interface. With a lithium sulfur battery, I assume, though without my own personal experience, I'll just put it that way, that the either or both of the anode and cathode in a lithium sulfur battery operate in a similar way to like a lithium ion or a sodium ion or something like that, where there's the formation of a solid electrolyte interface. And so this interface on the surface serves a couple of purposes, right? And then your question is, its stability affects the battery conductivity. Well, again, there's another sub question here, which is to say, are you asking about ionic conductivity or electrical conductivity? I'm going to sort of just make a few assumptions and try to answer as best I can, but my assumption of the question is something to the effect that, let me draw. I'll try to draw what I mean to, so I don't just talk into nothingness here. Just try to describe this process as best I can. So in a battery, roughly speaking, if I can draw for you. Okay, so in a battery, I have it's mostly at the anode, okay? So this would be anode on this side, right? So it's usually carbon material, right? I've got electrolyte here, right? I know it's not really water, but just go with me for now. So we'll have basically, whether it's lithium ion or lithium sulfur, I'll have lithium plus, and ions here. Okay. The interface that will form usually during the first charge discharge of a battery forms what's called the SEI. Okay. And so this layer right here is this interface or interphase. It's usually called SEI. Okay. So this is solid electrolyte usually phase, okay, or solid electrolyte interface. You'll see both of these used somewhat interchangeably, okay. Just making it bigger so you can see. So it's one of these two. So that's usually what this is. Now again, I'm sort of assuming that this is what you're referring to here. And as far as the stability is concerned, it actually is critical for the stability. Okay, so during the process of charging and discharging, lithium ions are either moving into the anode, okay, or away, right, towards the cathode, one way or another. Partially as a result of the large voltages associated with a battery, 3 to 4 volts or something like that, right? The electrolyte itself can often be subject to attack by the anode or the cathode, okay? And so this phenomenon of the SEI, what it actually is that the electrolyte itself partially decomposes right at the surface, and it forms this film. And so when this film forms on the surface, it actually is like the start of decomposition of the electrolyte. And that layer itself contributes dramatically to the stability of the battery. In fact, without it, the battery would be almost entirely unstable. And as far as how it contributes to the conductivity, like ionic conductivity, is tricky. I suppose I don't 100% know. Like, is it? It's not exactly the same as the diffusion layer. It's not. I don't know that how much people have, I don't know, differentiated between the conductivity in the SEI and the overall conductivity of the electrolyte itself. There's some conversation to be had there, probably. But the stability is the key here, because without the SEI, the anode would probably just rip apart the electrolyte as it's trying to pass lithium back and forth, and you would have a problem. Okay, so the SEI is actually a decomposition product that prevents future decomposition. And so that's I guess that's what I can say about it. And as far as other specifics related to lithium sulfur, or if you have a different question about a different kind of interface or a different kind of conductivity, you can try to clarify. But that's about as much as I can say as a very general answer about the SEI in a battery. Okay, I'll move on here to Fred. Fred asks, does a galvanostat work similarly to the potentiostat? It uses the feedback loop system and depends on the reference electrode. Right, so this is a good question. I actually don't know if I can explain it very well, to be honest with you. I did a webinar previously on potentiostat operation, for instance, and I know you're probably referring to that or wherever you've seen it previously as well, in terms of the feedback loop with the operational amplifiers. And I'll be honest, all I really know from an electronics or an electrical engineering perspective about galvanostatic operation is that it is fundamentally different, and I think it has a fundamentally different circuitry involved. So I'm going to say this with a very heavy asterisk. I think the answer is no, but I'm not 100% sure. Because fundamentally, it doesn't depend on the reference electrode, but the potential you measure galvanostatically is still with respect to the reference electrode. So in other words, if you have a 3-electrode system, right, and you run potentiostatic operation, then the potential that it's measuring and adjusting depends on the reference electrode. You obviously understand this. If you're asking this question, or I presume you understand this. In a galvanostatic operation, of course, because you're controlling current, it's not the case, right? And so having it be described as dependent on the reference electrode is probably incorrect. But but to the extent that you're running a galvanostatic experiment, you're controlling current and you're measuring potential. You're still measuring the potential between the working and the reference electrode. Now, if you have a 2-electrode experiment, of course, the reference and the counter are the same, as is often the case in a galvanostatic experiment. But if you're running a 3-electrode, like a regular 3-electrode experiment, and you have a regular reference electrode, then the potential that's reported by your potentiostat galvanostatically is still with respect to the reference electrode. So there's obviously a feedback loop galvanostatically as well, and the reference electrode is still part of it. Okay, but I do think that there is some fundamental difference in terms of the circuitry when a potentiostat's operating galvanostatically. I don't think it's the same diagram and loop, for example, that you may have seen either in my content or in anyone else's for how a potentiostat operates. And beyond that, I simply can't give you any more specifics. It's actually a little bit beyond my knowledge, to be honest. I'd have to probably pick the brain of one of our electrical engineers and see if I can figure that out, but that might be something for another time, because, well, to be honest, when you talk about how a potentiostat works, is you sort of talk about potentiostatically, and then you don't get into galvanostatically, because potentiostatic operation is more common, and I think it's frankly more simple. So to talk about how a potentiostat works, for those of us who have done those kinds of things, I know I've done it in my webinar, and my colleague Alex has done it, and a lot of our competitors have done it in different seminars and webinars I've seen. I don't know that anybody has ever really talked about galvanostatic circuit operation. Not to say it isn't interesting. It's just sort of like next level kind of stuff. And I'm actually not sure I've ever seen anybody describe it really thoroughly. But in any case, that's about as much as I can say for you. Let's see. Naresh has a question. Can you please explain difference between adsorption and capacitance in electrochemical sensing? Difference between adsorption and capacitance. So, I mean, the simplest answer is adsorption is something physically attached or bonded, physically connected to the electrode surface. Capacitance is not. Capacitance is a phenomenon where you have opposing, you'd say plates, but basically oppositely polarized or charged, one positive, one negative, typically, geometries, plates, layers is probably a better word, some distance from each other. And in that distance in between is some dielectric material, which is in electrochemical sensing, it's usually water or whatever electrolyte or fluid you have. And so the fundamental difference, of course, is just I suppose that one involves something physically touching the surface and one does not. and Chris also followed up that you can probe them with impedance. Yeah, capacitance is quite easy to probe using impedance as well, which is pretty nice. You can use a capacitor or a constant phase element, and yeah, it works quite nicely. Probing adsorption in impedance is a little tricky. There's probably ways to do that. I don't know. I'd have to think about it a little bit more. But in any case, impedance is a good, good start for probing these kinds of things, especially capacitance. Okay, Bill has asked an EIS Nyquist fitting, how to determine which circuit to consider if using different components can lead to the same fitting of the circles. I think this was a question. I think someone, perhaps it was you. I'm happy to talk about it again. I think there was, this happened last week, or was this on a YouTube comment? Someone had asked something similar to this. So let me try to give one practical example from one of my impedance webinars. This might help kind of address it. So the short answer, honestly, is you must have some knowledge of the morphology of your system, okay? So here's, let me pull up one example here for you. Okay, so this is from my second impedance webinar, okay? So for instance, if I have an interface, okay, of some electrode and some electrolyte, green and blue, right? The most common kind of thing to put there is a Randall's element. And so I have a CPE or a capacitor and a resistor. So I have charge transfer resistance and I have some capacitance, interfacial capacitance, double layer capacitance, whatever you want to call it, okay? If I have two interfaces, then I most commonly can put two Randall's elements in series. But for instance, there's a variation of this kind of circuit, right, where I have two interfaces. I might have two semicircles, right? A variation of this is what you might call an embedded model. And so you see this is a similar variant to what I just showed you, except now I kind of have this second Randall's element is like embedded in the first one, okay? Now, graphically, they can look almost the same, right? So this is where, to the heart of your question, I've got basically different circuits can fit the same data. I have like two semicircles. Well, should I put the second one embedded or not, right? Well, here's an example why you would use an embedded model, okay? So just get this animation for you. So I think this is the one without animations. Anyway, let's say I make a thin film on my surface, right? Okay, I have a glassy carbon electrode here, and I deposit some ink and I make a film on here. Okay, what I can have is I could have this, where I have the film fully covering the surface, but I might have instead a porous film like this. And so if I have a porous film, then some of my underlying substrate is exposed, all right? Another way to show that, and again, I'm jumping around a little bit here, this one. Another way to think about that is the difference between these two, okay? So for instance, if I have substrate here, film, and then electrolyte, right? You could see I would have one interface between the purple and the yellow, and then a second interface between the yellow and the blue. Alternatively, if there's exposed substrate, I might have a situation like this. Just get rid of this for a second. So I could have substrate and film, but I could also have electrolyte that touches the substrate, right? So this is the difference between whether it's porous or not. And so all I'm saying here to you as just a specific example, but the point of this is to say you want to know something about the morphology of your electrode and your situation, because the substance of your question is actually more deeper than this, right? For instance, you can fit an almost infinite amount of circuits to almost any data set, right? There's almost no limit to the amount of things you could. Now, eventually, you run out of 50,000 different Randall's elements. It's too overspecified, but for the most part, you can fit almost any amount of things. Okay, and so the reality is that you want to find the simplest model that still applies physically to what's happening. And so, when in doubt, my strategy or my suggestion to you for a strategy is to draw physically the microstructure like this, simplified, as to what is physically there, if you can. And then that might help you determine how many interfaces there are, how many of them are relevant, for instance, and then whether I should put circuit models at each of them or some of them. And that might help guide your decision as well. Okay. All right, let's see here. Try to move on. So Syed has a question. When anything is imaginary, how can it be plotted on a plot like in the Nyquist plot? I think there was a, I think there was a bit of a follow-up here. Yeah, Amir had a question. I think it's a similar, I guess this is a different person, but it looks like similar questions on, it looks like the same picture. So I'm not sure if this is the same person. But why is it called imaginary if it is frequently dependent? If it is frequency dependent impedance, if something is imaginary, how can it be plotted in Nyquist plot? Yeah, the answer to this is mathematics. It is 100% mathematics. So I have often talked about this on this exact live stream, and I haven't shown it. And so I usually don't show it because not everybody loves math. But I'm going to throw caution to the wind and go through the math relatively quickly. So this is a mathematical theory article that I wrote some time ago, right? And I'll walk you through it somewhat quickly, but hopefully you can appreciate a little bit. The answer to your question is just math. Like there is no other answer. The word imaginary doesn't mean it doesn't exist. The word imaginary is referring to complex coordinates. That's it, complex coordinates. So if you've studied mathematics, calculus, is it algebra or calculus? Anyway, one of those. You go over like the square root of -1 is the imaginary number I or J. And that's literally all it is. Okay, so the word imaginary throws people into a bit of confusion because of course the word imaginary makes you think it isn't real, it doesn't exist, it's made up, and that's not the case. It's just the English word doesn't sit well with people, I think. Okay, so I'll try to explain. Right, so the input of impedance experiment is a sine wave in this form. E of t is equal to E naught cosine of omega t. Okay, so we have angular frequency, time, amplitude, and then a time-based potential. All right, the response is if we input potential, the response is current, and this is the response. Current as a function of time has its own amplitude. It is also has the same frequency, and it might be shifted. This is the phase angle. Okay. Now here's where the imaginary comes in. All right. We use what's called Euler's formula. Okay. This right here is Euler's formula. This equation right here. You can Google Euler's formula. You can find the Wikipedia page on it. This is just a straight mathematical definition. E to the jx, j meaning the imaginary number. I don't use I because I is current in electrochemistry, but it's the same thing. Is equal to cosine of x plus j sine x. This is just a straight definition mathematically. Okay. So quite literally, all we do is take Euler's formula and we do some manipulation. We multiply by a constant on both sides, okay? This x here is just some angle. We substitute in this angle right here. This is the angle of interest, omega t minus a phase angle, okay? Or plus a phase angle, okay? So we basically just plug in this arbitrary angle, we multiply by a constant, and we end up with this expression. Now, this is the left, and we rearrange it. So the left-hand side here, I have cosine, and the right-hand side, I have some imaginary numbers. Now, again, I'm walking through this. This is just mathematics, so apologies if this isn't maybe your favorite topic and it's a bit confusing. When we have an expression like this that has a lot of terms, some of which are real, some of which are imaginary, we aggregate the real and the imaginary terms. And so the real on one side has to be equal to the real on the other side, and then the imaginary on the other side as well. And so basically you can see I'm just sort of reiterating what I wrote here, which is to say that we equate the real portions on both sides, and we get this expression, which is to say that the real portion of this side is equal to the real portion of this side. This part is all imaginary, so it goes away. So we end up with this is all a real. There's no I here or J, right? And that's equal to the real part of this. And then we just do some rearrangement. There's some simplification in terms that are substituted in, I guess. And what we end up with is a simplification in this form, okay? And what it allows us to do is to rewrite all the way back up here these two expressions for the potential and the current based on all of that manipulation I just did with Euler's formula, okay? So basically the long and short is that cosines and sines trigonometrically can relate to each other through Euler's formula, and they're cast into the complex plane. And so when we do that mathematically, we just end up with real and imaginary components, okay? We define the impedance this way, and the reason why we used Euler's formula is so that this can be simplified, because we have to divide E divided by I, and when we have our terms simplified this way, what we end up with is basically this oversimplified expression here. So you can see that Euler's formula basically just shows up in the expression for impedance. We have cosine plus J sine, okay? And again, it's just mathematics. The other thing that Chris has just brought up here is also true. It just happens to be the case, but basically imaginary impedance is related to energy storage. Basically, a shorthand way of looking at it is that the imaginary component is related to the capacitance, how out of phase your signal is. The real component is related to resistance, energy dissipation as heat, and resistances and how in phase it is. Okay. Again, my apologies if that was a little bit, I don't know, confusing if math isn't your favorite topic. But unfortunately, the only real answer to the question, why is there imaginary impedance, is mathematics. So I would encourage you, if you want, I'll put the link to this. This is EIS Math Theory. I'll put the link to that page in the comments, in the chat, so you can review that mathematics if you want to. And that's where the imaginary impedance comes from. All right, let me back up here and try not to miss anything. Got that one. All right, so Ur has a question. Can you explain the role of CPEs, constant phase elements, in equivalent circuits? Also, what happens physically to the electrolyte when doing electrochemical impedance spectroscopy? I mean, for example, do you first give a high frequency and, sorry, I lost my place. Do you give a high frequency and ionization is achieved, and then the ions move toward low frequencies and diffuse, or something else? Greetings from Turkey. Well, thank you. I'll answer the second part first. I think physically what's happening to the electrolyte when you're doing impedance is it's sort of doing this. It's shifting back and forth. I guess I have to think. It probably depends more precisely on the set point. So for example, if you're doing impedance at open circuit potential, and it's not drifting around, it's not moving too much, then probably in theory, when the sine wave is positive, like in the upper part, there's a slight positive current, and then down it's a slight negative current. Probably physically what's happening in the electrolyte is relatively, I should say, probably relative to the speed of whatever sine wave is occurring, the electrolyte is pulsing back and forth to some degree. I'm not 100% sure, though. I don't know that anybody has like visualized that. It's a good question though, but the I think that the other way to maybe think about it is that at low frequencies, because the sine wave is slower, right, up and back, it is allowing more time for the electrolyte or reagents in the electrolyte to move, to diffuse, which is a somewhat slower process. And that's why you're probing diffusion at low frequencies. Because again, I've sort of mentioned this this kind of phenomenon before, but impedance is probing phenomena that are occurring at the same time but on different time scales, right? So you have oxidation and reduction occurring in addition to the electrolyte or the reagents being drawn or repelled from the surface or whatever, and you have diffusion occurring, and you have capacitance build up. You have all the things happening, but they're all happening at different speeds. Like a capacitance sets up at a certain speed, and the charge transfer process happens at a certain speed, and diffusion happens at a certain speed, and some of those are faster than others. And so by changing the speed of the frequency of your sine waves, you're able to probe each of those processes separately. And then the role of CPEs in equivalent circuits. So in general, I would say it's non-ideal capacitance. So some people have real philosophical problems with CPEs because they're not real, so to speak. It's an engineering kind of tool, if you will. Right? The best justification I can usually provide for the use of a constant phase element is that even a perfect capacitor is not perfect. If you do impedance on a perfect capacitor, the Nyquist plot should be a straight line, and it never is. It's always somewhat tilted. And that is because a perfect capacitor is two perfectly parallel plates at some distance from each other, right? But the reality is that maybe the surfaces are heterogeneous. Maybe they're not perfectly parallel, right? If any of those things occur, you might still have capacitance, but it might be not behaving exactly ideally. And so to a certain extent, the best I guess I would say the best explanation for a CPE and its role and its purpose really is to capture this kind of non-ideal behavior, and the extent to which that parameter in the CPE, the alpha or the exponent, is less than 1 is the extent to which this capacitor is not ideal. So that is what I'll give you for that. And then it looks like Chris said 3 blue, 1 brown for some visualizations of complex numbers and more math fun. I don't know. Is this like a like a simulation kind of a thing? I'm not familiar with this. So yeah, maybe they'll have a visualization of like what the electrolyte's doing or something like that. So yeah, that sounds kind of cool. And a perfect capacitor would have infinite planes. Yeah, exactly. So even then, the edges mess everything up. Yeah, so if you have a perfect infinite plane, perfectly flat, perfectly parallel, you'll get a perfect capacitor. But that doesn't exist in real life, so let's keep using CPEs. Yeah, that's true. Okay, let's see. Let me go back to where I was after Ur's question. Okay, Sutan has asked, we know hydrogen ion has ionization energy of 13.6 electron volts. I didn't know that, but I'm glad that you do. Electrochemically, hydrogen ions have 0-volt references. It means no energy is needed to take 1 electron. No, that's not what it means. The 0-volt reference for the hydrogen reaction is arbitrary. It is chosen by all of us brilliant electrochemists. That is not what it means. It doesn't mean that it takes no energy to move an electron. If it did, we'd have infinite energy by now, and we wouldn't have to worry about our power grid and anything. The line in the sand, if you will, for potential was decided a long time ago to be the hydrogen reaction. H plus 1 electron goes to or two hydrogen protons plus 2 electrons gives you hydrogen gas, right? That reaction was decided a long time ago to be the reaction that is at 0 volts, but there's no reason. That's not true. There's, let me put it this way: there's no reason why it couldn't be anything else. We just chose that arbitrarily. Okay. So that doesn't mean there's no energy involved. It just means that everything else basically, is with respect to that. So when we say, like, it's 1 volt for this reaction, it's actually 1 volt with respect to the hydrogen reaction, because all voltage and potentials are relative. It's not an absolute quantity. It's a relative quantity. So that's just what we chose to be 0 volts. But no, there's still energy. And I guess this ionization energy, I don't know. I take your word for it. That's the correct ionization energy. I don't know that number off the top of my head or anything like that. But no, there's obviously energy still required, as with anything, to take an electron away or, associated with giving an electron to a species. Okay, Sutan's question, Ur's question. Yeah, so Chris was commenting on a galvanostat. A galvanostat will servo the current using a feedback loop over a fixed known resistor, potential measured with respect. Yeah, so like I said, the potential is measured with respect to the reference electrode. And the current over a fixed known resistor, that's similar phenomenon to the potentiostatic operation, which is to say you measure the current by passing through a resistor, and we use Ohm's law. So it's a similar phenomenon. But I think that again, just the point of it being the feedback loop it's somehow different than the typical one that I've shown for potentiostatic operation. But in any case, future stream idea, drag one of my EEs into the discussion panel. I'm not sure they would want to do that, but I think they would be bored by most of this discussion. But yes, that would be useful for conversations like this. The other problem is, I mean this as a compliment as best I can. If I brought my my electrical engineering colleague into this discussion, he's way too smart for this. When I talk with him, a lot of times what you get out of me in a webinar or in this live stream, I had to talk with our electrical engineer, one of my colleagues in particular, and I have to like talk to him and ask him the same question multiple times and distill it into a way that even I can understand. It's very complicated, and he's so brilliant. I have a hard time sometimes grasping exactly what's going on electrically. It's a very interesting phenomenon. I can tell you, for instance, if you're in academia right now and you're wondering if you're going to go into industry or stay in academia, one of the fun things for me, having been in academia as a postdoc and then I'm in industry, is learning this side of electrochemistry, like how the instruments work electrically, those kinds of things. It's not anything that I had any practice or knowledge of, before I started working at this company. And now I've learned a lot, but there's still so much stuff that I don't really know, of course. And it's fascinating to kind of learn that aspect of it. And some of you may learn that already, or maybe you have an interest in it. Lots of people build their own potentiostats or whatever. On their own. But for me, I didn't have any kind of knowledge of that topic really before I started working in my capacity now. And it's fun to learn some of those kinds of things, but it's definitely quite complicated. Okay, Sutan has another question. Let's see. Can you say fundamental difference between electrochemical capacitor and battery work? Fundamental. I think you're asking what's the difference between a capacitor and a battery. I guess is that I think that's what you're asking anyway. Let me just follow up and see if there's any other. So anyway, I think that's what you're asking. So both a capacitor and a battery are storage devices, right? A capacitor, electrochemical capacitor, or a supercapacitor, whatever terminology you're using, operates with the phenomenon of capacitance, which is what I have just described a little bit ago, right? Is the theory of two infinite plates. Thank you, Chris. No edges, but right, basically two plates, some distance away from each other, opposite charges, plus and minus, and there's something in between, a dielectric material. This is the definition of a capacitor, and it is a means to store energy, store potential energy. And fundamentally, I mean, it operates on that phenomenon, I guess. Capacitance is a phenomenon. It's like an observable phenomenon. I don't know how to describe it anymore. It's an observable phenomenon when you have that structure, that energy is stored, right? And it's stored proportionate to all the parameters involved, right? The amount of energy you can store is proportionate to the what dielectric is in between, how far apart the plates are, how big the plates are, how ideal they are, what materials they're made out of. All those kinds of things impact how it stores energy. And then a battery is an electrochemical device that also stores energy, but through a slightly different mechanism. It's basically through the, let's see, how would I word this? Through the potential difference between two sides. So both involve two sides, right? A capacitor has two plates or two opposing, layers or whatever. A battery is similar in that way. There's an anode and a cathode. There's two different sides, but the way it stores energy is through the potential difference between each side. There's a better way to word it than that. Essentially, the storage occurs because, like in the case of a lithium battery or a sodium battery, is that an ion or a species is aggregated in one side, and the voltage associated, the fundamental thermodynamic energy difference between the two sides of storing that material is positive. It's some number. It's some amount, and so it's working with thermodynamics which is the difference in the standard potentials, and and then the amount that the battery can store is in a similar way related to, just like a capacitor in a lot of ways, the materials used and the properties associated with them, and also how much of them is used. Because in a battery, for instance, you make a lot of, if you have a certain amount of energy can be stored between these two materials, if you get a lot of them and you stack a lot of them next to each other, you can store more energy, right? Similar kind of a thing with a capacitor as well. But if that's roughly what you were asking, I hope that's it. So yeah, this is another good succinct kind of answer. Chris says, in a capacitor, you're generally not working with chemical reactions. Not always exactly the case, but I understand your point. A battery is chemical reactions, right? So it's a capacitor, like an electrochemical capacitor, of course, is just chemical reactions. But yeah, a battery moves charge, a capacitor separates them. I mean, there's still charge buildup in a capacitor, but yeah. So fundamentally, both are energy storage devices. They're both used pretty relevantly everywhere, right? And in many cases, they're used for slightly different mechanisms. I guess you'd say, generally speaking, capacitors tend to be better at discharging very fast, whereas batteries tend to be better at discharging more slowly over a long period of time. And so if you need a short burst of energy, a capacitor is usually better. If you need a longer, in a longer term dispelling of energy, or slightly less, a battery is usually better. And yeah, and the supercapacitor Faraday process is also there, right? So that's what Chris was saying. In some cases, it's true. There's not always chemical kind of reaction. It doesn't have to be a chemical process in a capacitor, but in an electrochemical and a supercapacitor, you can also have that. But I guess in general, I suppose, Sutan, I don't know, maybe you're correct in some cases, but for the most part, capacitors are classified as non-Faradaic. So that's typically the case. Now, I'm not an expert, perhaps I'm not classifying something exactly correctly, but usually we call capacitance a non-Faradaic reaction, just for what it's worth. But anyway, I will move on from that, and let me find where I was. Imaginary impedance, fundamental difference. Okay. Alex has a question. Why can the slope of the line in the Koutecky-Levich analysis be 20 to 40% smaller? Is it okay in this case to interpolate to an infinite RPM and calculate the kinetic current? So can you extrapolate to infinite RPM in a Koutecky-Levich analysis? I think so. Hang on. Let me pull up something here and look for a moment, because why can the slope of the line in the Koutecky-Levich be 20? See, I guess the first part is I don't 100% know what 20 to 40% smaller than what? Koutecky-Levich. So just to be clear, Koutecky-Levich, a plot of Koutecky-Levich is 1 over, let me say the right order, right? 1 over 1 over the square root of the rotation rate versus 1 over the current. I think I said that backwards. But in any case, the slope is 20 to 40% smaller. First of all, I don't. Yeah, I guess I don't understand. What do you mean smaller than what? What is that in relation to? And then, is it okay to interpolate to an infinite RPM? So the infinite RPM would be. Let me pull it up here. So this is This is the Koutecky-Levich equation. I'll show it while I talk myself through this with you here. So, smaller than the theoretical one. Sorry, you did clarify. Smaller than the theoretical. So first of all, if your slope is smaller than the theoretical one, it could be that you have some fundamental error in the measurement, right? You might be not your data might not be I'll say one of two things. Your data might not be diffusion controlled enough to have the Levich equation be accurate. I would say something like that, and or the data itself in general might not be behaving ideally, right? Because Koutecky-Levich analysis requires some assumptions, like it requires a one electron irreversible equation process to be occurring. The geometry of everything has to be perfectly. The hydrodynamics have to be such. Now, in a lot of cases, we just make that assumption anyway. But my point is that in some cases, it's not exactly accurate, all of those assumptions, and that could be leading to some of these errors. So that could be at least behind your observation of the slope being off, let's just say. Now, in terms of interpolating to an infinite RPM, infinite RPM for the Koutecky-Levich expression or equation means this. So we plot the inverse of the current against the inverse of the rotation rate, and so the extrapolation, it's not interpolation, it's extrapolation to infinite rotation rate is when this goes all the way to 0, right? So that would be the that isn't that just that is the answer. Yeah, I'm sorry, I'm overthinking this. I'm just trying to make sure I say the right thing. The kinetic current is basically what you're saying, if I'm understanding you correctly, which is to say, at infinite rotation rate, right, 1 over infinity is 0. So this term goes away, and effectively the current is the kinetic current. So basically the kinetic current is the y-intercept. So yes, that is actually fundamentally what we're doing with the Koutecky-Levich equation, is finding the infinite current, so to speak. The infinite RPM, which corresponds with the kinetic current. So yes, I think if I'm understanding your question correctly, that is correct. That is what you're doing. And then hopefully, if you need to keep using your data for Koutecky-Levich, but your slope is off by a little bit, you either want to repeat the experiment and try to just it's hard, right? The RDE experiments, it can be just fundamentally difficult to get accurate data. It is normal to have a bit of error, and to a certain extent, there's actually nothing wrong with acknowledging that there's some error with this, but it's okay, if that makes sense. Like you can say, oh, there's some it's smaller than anticipated, but there's this A, B, or C reason for that. In fact, the slope of Koutecky-Levich specifically, just to go back to this really quickly, being off from theory is very often what happens, in my opinion, because of the fact that the slope, which is related to this, it's been related to the Levich part of the Koutecky-Levich equation, right? The slope is basically containing of the diffusion limited current, right? Because the Koutecky-Levich equation, is basically the combination of the kinetic and diffusion limiting currents. Now, if you follow the way this works, of course, is that we substitute in the Levich equation for the diffusion limiting current, and that Levich equation information is what contributes to the slope. And then follow me here that the Koutecky-Levich analysis is performed usually in this region, for instance. Okay, so these regions of interest where I'm taking Koutecky-Levich data to make the plot and get the slope are not the diffusion limiting regions. So I'm actually not always that concerned or surprised that the slope is not ideal. For example, getting the diffusion coefficient or diffusional information from Koutecky-Levich is not always the best. You want to use just the Levich, because in the Levich analysis, you take diffusion region data. With the Koutecky-Levich, you're taking the sort of transition region, if you will. Okay, and so it's not unusual to have the slope, but for the most part with the Koutecky-Levich, you are really only interested in the extrapolation part of that. And so yes, it's okay to do this extrapolation if the slope is not as theoretical. Yes, I think it is, because I'm almost always less concerned about what the slope is fundamentally because of what I just described. The data I'm taking that contribute to the slope of the Koutecky-Levich plot are from diffusion limited information, and I'm taking the data not where it's diffusion limited. So I would expect there to be some error associated with that, but it's sort of by design. This is just how the Koutecky-Levich analysis is designed. It's kind of murky. You're taking diffusion limitation. You're taking the theory that both diffusion and kinetic information are present, and you're taking over a range of potentials, but it's not really diffusion limited. So I'm not surprised to see some error with the slope. And yes, I think it is reasonable to still extrapolate to get your kinetic information. That's kind of the purpose of the Koutecky-Levich. So I would suggest that you proceed. I think you're doing it correctly. It's my impression based on your questioning. Okay, Parth has a question. If reference electrode gets damaged, the CV peak potential gets shifted, but why does the current density decrease? So you're saying the peak potential is moving because your reference electrode's damaged, and then why is it also impacting the current density? That is a good question. You know, I think the short answer is probably that there's more going on than what you're maybe thinking. You know, if it was as simple as the reference electrode's damaged, and the extent of the damage is that it is causing everything to move by 100 millivolts or something, and that's it. That's all it's doing. And then you would see the exact same CV just moved over. Then that would be probably what is happening. But very possibly something else is going on. You know, the reference electrode being damaged might be causing other side reactions to occur, might be causing your you know, the potential with which your potentiostat is applying because it isn't sensing properly. It might be impacting the working electrode. You know, you might be destroying a film or something like that. There's probably more going on here, to be honest. I don't know that I can speak more specifically to this because obviously I'm not looking at your data. I don't 100% know what's going on, but I think most probably there's more going on than just the reference electrode. Like for instance, if you have a silver chloride reference electrode and it has 4 molar KCl, okay, then you change to like 0.1 molar KCl, you'll get a shift of like 100 millivolts or something like that. It's like 60 millivolts per 10x, something like that, whatever. concentration, but it's the Nernst equation. But Alex isn't here; it's his favorite equation, and I'm talking about the Nernst equation. So hopefully he sees this later and gets very upset he wasn't around to talk about the Nernst equation. In any case, my point is, if you take a perfectly functioning silver chloride reference electrode and you change the fill solution, you will get the behavior in theory that you're describing. Everything is the same; it's just shifted. But I think probably if you have some real damage to your electrode, something slightly different is going on. And so it's changing something about the working electrode, or its behavior, or something is going on. And so the situation's probably a little more complex that would, lead to you having a different fundamental response, like the current density is different, everything like that. Okay, let's see. Chris is helping out with some of these questions I'll get to as well. But I'll move right along. Divya has a question: how to calculate the value of alpha in Z calculation of circuit fitting? How to calculate the value of alpha? So I assume you're talking about, wait, I don't know if you're talking about, alpha is normally the exponent in a constant phase element, which is the degree of non-ideality in a constant phase element. I think you mean one of two things, and I'm not sure which. Let me see if I have, not that one, not that one. Let's see, do I have, so for a constant phase element, okay, so again, I'm not sure what you are referring to exactly. If you're referring to the constant phase element, I think I have it defined. Right here, sorry, I pulled it up. So this is normally what alpha refers to, is the constant phase element. And so if you're talking about it here, this is the non-ideality factor. And there isn't really an answer of how to calculate it. It's a fitting parameter, which is to say that when you do circuit fitting, the algorithm, the software calculates what alpha is for you. That's fundamentally what it's doing. Okay. And it's usually between 0 and 1, more often between 0.5 and 1. If, however, what you're talking about is the chi, what's commonly called chi-squared, which is the goodness of fit, basically, error statistic, you might be asking about this, which I'm not sure. And very often this kind of parameter is calculated something like this. It's basically the sum of the difference between the fitted points and the experimental data. So for example, in this case, something like the dots are my experimental data. The line is my circuit fit, and at all points there's a distance, or some distance between the two, and how far away these are squared and summed and averaged and added up. That's the error statistic for a fit, and that's also just calculated by the software. But that's roughly, there's some specifics exactly for how these are calculated, but that's roughly how that's calculated. So again, I don't know which one of those you meant precisely, but if it's one of those two that you're referring to, Divya, then hopefully that answers your question. All right, so Chris has a question, not my colleague Chris, colleague sitting host in the chat, I suppose. But I have to do a CV in aqueous medium. In order to do that, I need to check the GCE's reproducibility. For that, I have ferrocene only. What can the supporting electrolyte used other than TBA? TBA HP, what's HP? So TBA, usually use TBA PF6. TBA, P electro. I just don't know what HP is. Is it perchlorate? TBAT. So typically people use TBA PF6. I don't know if that's what you're referring to. That you don't have that. Let me see. I don't know if Chris, my other Chris, had some suggestions. Maybe not. So you're using ferrocene. I'll be honest. I don't know what else people use besides TBA PF6, and I don't know what TBA HP is. Nothing's coming up when I search for like TBA TBAP TBAP. I think there's some. I'm not sure what the P. Maybe that's just PF6. I think typically it's tetrabutyl ammonium hexafluorophosphate. I don't know what else, but is typically used as a supporting electrolyte. I'll be honest. I actually am not 100% sure. I have not done a ton of non-aqueous electrochemistry, at least when I was like in graduate school, apart from battery stuff, which is sort of its own animal in terms of what electrolyte you use. I wonder if anybody, I don't know. Yeah, Chris, I don't know if you know of any other supporting electrolytes for like acetonitrile. I really am only aware of TBA PF6, and so I don't know what TBA HP is, if that's what you're referring to. But I don't think I have any suggestions for you. Unfortunately, I don't know any other ones, unfortunately. But hopefully you can get TBA PF6. I mean, that's the most common one, right? It's a really good supporting electrolyte, and it doesn't interfere, and it's great for ferrocene redox. Sutan has another question. Can we say more area semicircle in EIS is good for energy storage? Not necessarily. If you're referring to like the Nyquist plot, the semicircle area is not exactly a parameter you are looking at. I would say to a certain extent as well. A larger semicircle is in the context of a energy storage device like a battery or a fuel cell is often a bad thing. The reason being that the width of the semicircle is proportionate to the charge transfer resistance. So a bigger semicircle means a bigger charge transfer resistance, which means it's worse. It's like the resistance is higher. You're getting less energy out of it. So a smaller semicircle perhaps would be correlated with a better energy storage, or at least energy delivery. The resistance with which you can get energy out should be low so that it's delivering energy very easily. But the capacitance is what you're talking about in terms of how much it's stored. So that if you're measuring the capacitance, and let me just illustrate for you in our software here. So this is my company's software, Aftermath. So for instance, here's a zoom out so you can see. Here's like just a simple Randall's element, redox, whatever, a semicircle. I'll zoom out. So if I increase the semicircle or decrease it, it is just increasing or decreasing this resistor, right? So the resistance is going down or up. So you'd say that the area of the semicircle is getting bigger or smaller, right? I suppose, depending on how big this is. But again, it's actually the opposite, probably, if anything, that the smaller the resistance, the smaller the semicircle, the better it is at getting energy out. And then this up here, just to illustrate for you, is the capacitance, the CPE here, but you can think of it as the capacitance. By changing the capacitance, Watch what happens to the semicircle up here, right? So here's the semicircle. Watch what happens to the semicircle when I increase the capacitance. Nothing, or at least you don't see anything. Okay, it moves the Bode plot. You can see it moves basically the dip in the phase angle up and down, the frequency axis. If I go to the extremes, the semicircle either doesn't finish or doesn't start. Okay, but basically the semicircle width is unaffected by the capacitance for the most part. And so what that means is that if you're going by the width of the semicircle or its area, it will not give you any indication of a difference in the capacitance. So you would not use that as a metric, probably, to gauge the storage situation of your battery or your capacitor. Okay. Oh yeah, Chris followed up this 3 blue 1 black. It's a math white YouTube channel. YouTube will reject it without a blue wrench. That's weird. More YouTube stuff. Yeah. Anyway, yeah, if you're looking for mathematical simulations, go to, what is it? 3 blue 1 black. Is that what it is? 3 blue 1 black. I hope I'm not promoting something strange. I've never heard of this, but I blame Chris Georgie if that's the case. 3 blue 1 brown, not black. 3 blue 1 brown. So anyway, that sounds cool. I might check that out later. Okay. So Yuvraj, Alex is not present. Unfortunately, he is out this week. It might be a few weeks before Alex is back. So you only have me today. So if you need Alex, you're going to have to wait a little while. Very sorry. Let's see. I think Chris was following up here. He had asked the question before about TBA, energy conversion device, power density. Oh, it's just similar to the previous question, I think. Okay, let me find where I was. Okay, Nikhil, and I think Chris was helping out as well. So how do we confirm or check if the mercury oxide electrode is damaged or not? I'm getting inconsistent readings from CV, galvanostat charge discharge, which was previously not the case. And you said you're using 6 molar KOH. So Chris asked about glass. You don't have any glass. Yeah, so Chris asked this question, which is usually the first thing that we tend to suggest, which is to check the reference electrode in a well-known system with known confounding factors. If you have another reference electrode that you can test it against, you have like a master reference electrode you never touch that you know is working, even if it's not an alkaline one, checking a reference electrode against another one, it won't take that long, even if there's glass, all this kind of stuff. You can do it relatively quickly. So if you have like a silver chloride or a calomel or whatever, you can probably just put them both into some beaker and check the voltage between them. And the main thing is to make sure is, right, of course, that the value of your HGO is roughly, it's about 100 millivolts versus SHE, or versus NHE, excuse me. And make sure that it's not drifting over time. So if you're measuring the voltage, the potential open circuit between your problematic mercury oxide and a good one or whatever, make sure it's not moving over time. And so you said you checked ferrocyanide redox. Electrolyte was 4.24 molar, cell concentration. Yeah, I think that, let me see. The drifting thing to me is the main one. So having the set potential be slightly off only would shift things. That would be like that situation I talked about before. If things are shifted by a little bit, probably it wouldn't be a big issue as long as you know what the potential window is supposed to be. But I think the inconsistent readings seems to be an indication that it's moving, that it's drifting over time. So refreshing the fill solution, things like that can help. The issue, of course, which hopefully isn't the case, but can happen depending on, I don't know, certain situations, is if the mercury itself is contaminated. For example, if chloride gets too much chloride got into the mercury oxide compartment, it might form some calomel, and then you'll have a bit of a heterogeneity in your reference electrode, and that can cause inconsistencies in the data. And the problem is mercury amalgamates with a lot of stuff, right? That's what calomel is. That's what mercury oxide is, mercury sulfate. So it's tough to undo that if that has happened. And one of the problems with a mercury oxide reference electrode fundamentally is that because it has no glass, a lot of times the frit is something like Teflon or polypropylene or something like that, and it's a little more porous. It has a higher leak rate. It can be harder to just keep contamination from them. They're a bit more finicky in general, and these are just tricky things to contend with. So, trying to think if I have any other like advice. I mean, it does seem like you're doing most of the things right. I mean, if you're checking it against something, but ferrocyanide isn't the best redox couple to test it against. Ruthenium hexamine is a little bit better, especially because, again, I don't know, ferrocyanide is a bit inconsistent, but yeah, checking for glass. Honestly, I'm not sure what else there is to do, but to make sure you're checking if it's drifting before every test. Check the drift over like 20-30 minutes time and make sure it's not moving its potential, because probably if the potential's moving around during your test, that's the problem. And then if all of this isn't working for you, you might have to resort to using a different reference electrode. Even one that has some glass, you could try using like a salt bridge, like a tube, like you get a plastic tube and connect that to something that's in a separate container. If you have to use something like calomel or silver chloride, a reference electrode that's a little more well behaved, you might have to resort to something like that. And then, I guess it is true that alkaline isn't generally advisable with glass, but that kind of dissolution happens very slowly. So if you have relatively short experiments or you're not doing really high temperatures, it might not be catastrophic to use a glass reference electrode if it's minimally dipped into the solution over a short period of time, especially if the mercury oxide one is continuing to give you some problems. Okay, so Nikhil, hopefully that gives you some direction, and hopefully you're able to kind of figure this out. Let's see. Joseph Michael says that we are an interesting channel. I appreciate that. We do try. I want to do electrodeposition of copper bismuth sulfide, I guess, Cu3BiS3. Okay, I am not sure of some of the chelating agent and the right parameters to use. Yeah, it's a really good question. Unfortunately, this probably qualifies as the type of question that's a little too specific for me to be able to answer. I mean, electrodeposition is a really fascinating and interesting topic, but the specifics of each individual metal, individual species that you would want to electrodeposit are I just simply don't know, right? I don't know all of these details. In fact, I don't know that I've ever really worked with chelating agents. I know that electrodeposition of, like, the most common one, for example, is like copper onto platinum, and then you can have accelerants or decelerants depending on how fast it works. I'm not sure if that's the same as a chelating agent, if it's like binding the metal ions or if it's just slowing down the kinetics or something like that. Unfortunately, I don't know that I can give you any more specific details yet, because this is just something that's like, I'd have to look in the literature. You might probably already be doing that. I guess the only general advice I can say for electrodeposition is something like, in a lot of cases, although it takes a long time, if you are electrodepositing at a very low current rate, you'll have a lot of times a really uniform film will form, right? So if you're depositing at a really low current or current density, your film will form more slowly, but it will be more uniform. And if you deposit at a higher current or current density, your film will be more structurally irregular. Even if you get more deposition done, it might not be the best film. So maybe that comes into play, but it probably depends more on your specific material, and I'm just not that familiar with it. So, oh yeah, so Yuvraj, you wanted to tell Alex that you passed your college entrance exam, and you're currently in one of my dream. I don't know what CLG is, or just one of your dream places. Anyway, Alex helped you, and I'm sure he'll be happy to know that you um, are doing well. Congratulations! We're happy to hear it for sure. So yeah, hopefully Alex will watch this later. If not, I'll let him know. Very nice to hear. Mike says, "How would glass interfere?" So glass interferes. I'm seeing if yeah, Chris kind of spelled this out a little bit. So glass slowly dissolves in alkaline environments, but again, it is very slow. And basically, glass is silicon, right? Borosilicate, so it's like silicon oxide. And over long periods of time, or really high temperatures, or really strong base, you can get small amounts of dissolved silicates in your electrolyte. And this is the other part. It may skew results because it also may not. A lot of electrochemistry is not particularly sensitive to silicates or silicon or anything like that. And so this is one of these things where I tend to take a bit of a different approach. The traditional electrochemist kind of common knowledge, if you will, is avoid glass at all costs if you're doing anything alkaline. And it's not bad advice, right? Use a Teflon cell, or I don't know, use plastic or something like that. It's not like it's bad advice. But I'll tell you that I worked almost exclusively in alkaline electrochemistry for like 2.5 years when I was in graduate school. Granted, it was relatively like low-ish, 0.1 to 1 molar like hydroxide. So not like 6 molar KOH. Okay, and I wasn't using like high temperatures. So I acknowledge that. But I used glass all the time, and it was not a problem. Now my electrochemistry was not particularly sensitive to small amounts of dissolved silicates or anything like that I'm aware of. So, my experience and my knowledge is a little bit colored by that experience, if you will. I just don't think it's that as big a deal as people make it, should I say. So I just try not to overreact about this. But yes, it is certainly possible that some silicates or dissolved glass could impact your experiment. But I think that the problem is somewhat overstated. So I just try not to overreact to this. If, like I said, if you have relatively dilute alkaline, relatively short-ish amounts of time, moderate to room temperatures, probably nothing's going to happen. So, okay. So Nikhil, yeah. So back to the mercury oxide, something yellowish coming out of the electrode, and you later found a crack in the frit. Oh, the frit dissolved. Yeah, something. That sounds like a worse problem. So probably you have a damage. Yeah, the frit was ceramic. Maybe it's causing it. Right? Yeah, it might be. Something seems really actually damaged, and the irregularity might be because you have inconsistent communication because of some damage. This would be a bit more of a diagnosis here, right? Than seeing some damage in the electrode physically. If there's a crack or something like that, that might make more sense, I guess. So okay. So Divya, you clarified. I think, let me go back to your question, remind myself what you had asked originally. calculating alpha. So you were referring to the non-ideality. What is the fundamental procedure to get the value? It's just a circuit fit. I guess I don't. Earlier, I was referring to the non-ideality factor involving Z of the constant phase element. Could you please elaborate and make a video on the fundamental procedure? So again, if your question is how do I get the value for alpha from a circuit fit, the answer is the software does it for you. This isn't something you calculate. I describe in in this webinar, for instance, which is in our YouTube channel. You can find it if you wish. It's the second week of my 5-part series. Let me find the slide. A constant phase element, the alpha value here is descriptive of what kind of element is there. So if alpha is 1, it's a capacitor. If alpha is 0, it's a resistor. And if it's -1, it's an inductor. But you basically can ignore that for the practical reasons. And so the fundamental procedure to get alpha is doing a circuit fit. It's the same procedure as to get the value for Q or for C or R. There's nothing special about the non-ideality factor compared to any other parameter. It's just one of the parameters that are obtained when you do a circuit fit and you have a CPE. I think perhaps you might be thinking about it in a different mindset, perhaps. The alpha value is just another parameter that is fit by the algorithm of circuit fitting. That's it. There's nothing more to it than that. It's not. I don't know. I'm not sure how else to kind of describe it, but it's not something that's calculated separately. It's just one of the fitted parameters. Like you have this circuit, right? You have whatever circuit you're using, and you have resistors and capacitors, and if this is a constant phase element, there's an alpha. Like the circuit fitting just fits all of those parameters. It's just one of the parameters. It's not anything different, I guess. I don't. If you still mean something different, perhaps you can clarify again. But I think you might have a slight misapprehension about what this parameter is. There is no fundamental procedure to get the value. It's another fitted parameter. Fred has another question: how to determine the right potential window for Mott-Schottky analysis? I get different results when I make the potential window bigger or smaller. So this is highly dependent on the material you're studying. The potential window that you pick. Let me pull up something really quick here. Sorry, give me just a moment. So in some cases, there's some strange stuff that can happen over different potential windows when you do Mott-Schottky, right? And that's because you are changing. I'm trying to find one bit of information. I'm sorry. Just give me a moment to kind of look through my records here, find what I'm looking for. Okay, so essentially, okay, so just as an example, if you're doing Mott-Schottky on a material, it has some sort of it's a semiconductor typically, right? And it has a majority carrier and a minority carrier. And so often what happens is when you're changing the potential, you're going through a region where you're either accumulating, depleting, or inverting that charge carrying situation. So, um, so it boils down to what you're trying to study. If you're trying to study, like, let's just say the material, like, uh, like fundamentally, I don't know, something like that, right? Like it's some material that has semiconducting properties, and you're not trying to study what happens when it's under extreme potentials and you're inverting the majority carrier or something like that. Then you probably need to pick a window. In some ways, you do this experimentally. So if you have a Mott-Schottky plot and it's like, sometimes it looks like an S, sometimes it'll sort of do like a dip and change directions. That's the inversion. Um, then sometimes it's just as simple as picking the potential region that is where it is. You sort of back your way into which potential window to do, which is to say, where is it most linear? It's kind of like what I've talked about this with TAFL, for instance. Sometimes, what's the potential window to do? Take your TAFL slope, do it everywhere, find where it's the slope that you want, like 120 millivolts per decade, and then that's the potential window you want. So in some ways, you can do a similar thing with Mott-Schottky. I think a lot of times it's good to take a big, wide potential survey to see the whole behavior. But I think in some cases, you um, change the potential so much that you change the charge carrying um, behavior, that it's not it's the material isn't acting like its original purpose anymore, right? You sort of, you go past flat band potential, and then you have an extreme depletion, and basically your majority carrier becomes your minority carrier. You have some kind of odd behavior like that. So, um, so again, just to reiterate, the first answer is basically to do something like take a wide window and then focus in where it's most linear, and that might be sort of a um, post hoc method of zooming in where you want. And the second is to, if you can, find a way to, uh, um, through literature study or just your own knowledge, whatever you want to say, um, uh, find the potential window where it's operating most like its semiconducting self, and not such an extreme potential that it's changing its oxidation state or it's changing its semiconducting properties. Because then it's like, well, if that's fine, if that's what you're studying, but if you're just trying to study the material natively, then you don't want to probably vary the potential too far beyond um, a small window, let's just say. Okay, let's see. Perhaps the question is, how does the fitting algorithm find alpha? Same way it finds everything else. Honestly, it's the same way it finds everything else. I mean, you can literally Google Levenberg-Marquardt or simplex. It's an algorithm. It's something like generate plot, have data, find the difference of error, change one parameter by a little bit, recast it, figure out what the error is. Change the parameter by a little bit, recast it, find out what the error is. The error should be minimizing, and it does. It's just variations of that. The alpha is just another parameter it changes while doing that. It's all the same. Okay. Uh, Someone has asked this. We covered this earlier, so I'd encourage you to go back in time. There'll be timestamps on this eventually as well. But I talked about this. Basically, the short answer is mathematics. And earlier in the chat, I put a link to the mathematics of impedance. So hopefully, if you want to check that out, you can. But I talked about this. Basically, you cast the sine waves using Euler's formula. You end up with complex plane mathematics, and that's why it's imaginary. It's not made up. It's not invisible. Imaginary just means complex numbers, a plus bi. That's it. Okay, let's see. I've got time for a few more. So Wynero says has a question about corrosion. So regarding corrosion of a metal sample in 3.5 weight% brine, sodium chloride, EIS spectra show the expected semicircle or semicircles. In rare cases, the data points in the low frequency region are shifted up and right. Up and right. Okay. So do you have any idea what this may be caused by? So far, I've assumed to be an artifact. It does not look like the usual scattering caused by corrosion. Frequency range, you're going down to 10 millihertz. That's quite slow. You've got the sample of your working electrode. Reference is calomel, counter is graphite. The first thing you should do is Kramer's-Kronig, because you said it doesn't look like scattered, but do Kramer's-Kronig for sure on your data. If you're not sure what Kramer's-Kronig is, I encourage you to look at Google it or check if your whatever software you're using has it. Our software has Kramer's-Kronig. Kramer's-Kronig is used to determine the validity of data. So if you're having some odd stuff at low frequency, first of all, up and to the right sounds like diffusion, but perhaps it's not quite like that, right? If you have semicircle and then it kind of goes off up and to the right like a tail, that usually means there's diffusional behavior. But the way you're describing it, it says if it looks like an artifact, it might be something a bit strange. It could be, you're going down to 10 millihertz. That's really slow. Drift is often something that happens at low frequencies. The data can be inaccurate at low frequencies. It does happen. And the quickest way to check is to run Kramer's-Kronig. And so what you might find is that the data fits pretty well to Kramer's-Kronig, but the low frequency doesn't track, and that would just be a good indication that it is some kind of an artifact. You might just disregard it, but that's my quickest. KK says data in low frequency is bad. Well, there's your answer. Yeah. So I think that there's not much more to say, really, honestly, that it's getting data at 10 millihertz is really hard. It might not be possible at all, but you can disregard the low frequency points and still use the other stuff. It's still okay to do that. It's basically like the semicircle is just cut off and then moves on, shifted up into, yeah. So this is just drift causing discontinuities in your data. So yeah, it is. Artifact is the right word if you want to pick a word that kind of indicates connection problems or hardware, reference electrode, cabling, slow data. In other words, it's not chemistry, right? So it's not something you need to explain the phenomenon like, oh, my electrode is doing this corrosion process is happening. It's not that. It's just an artifact. So good. I'm glad that you were able to at least do Kramer's-Kronig on it. If you have any other questions, let me know on it. But basically, I think you have your answer. I wouldn't sweat about it, to be honest. All right, let's see. Tato has a question. How to avoid high-frequency mutual inductance? High-frequency mutual. It affects my low impedance measurements for uncompensated resistance. Can this be eliminated or no? I use alligator clips instead of pouch cell clips. Right. So you tried looping the current and sense. Yeah, I was gonna say if you twist current. No, not. That's not the right. You wanna twist the sense lines and the drive lines separately. Is that right? Yeah, I think that's right. I think what you want to do, if you have 4 leads, like working, yeah. So working encounter, working sense, and reference. You want to twist the working. Excuse me. Yeah, twist the sense lines, the working sense, and the reference, and then twist the drive lines. Twist the counter and the working drive. Twist those separately as much as you can on their way to the leads. That can help. And then yeah, Chris has some other good minimize the length as much as you can. Make sure there's no loops, but the twisting can help reduce that a little bit. Let's see. I have 5 channels in the potentiostat. Pouch cells cycling on other channels. Do you think this may cause the inductance? If I have 2 channels doing EIS simultaneously, my measurements are weird. 2 channels doing EIS simultaneously. If you have 2 channels doing EIS simultaneously and your measurements are weird, that sounds like something strange with the hardware. Like if you have 2 pouch cells and you physically move them, if you can, away from each other, does it change or does it improve? Because it sounds like the likelihood that there's like interference going on like in the air between the two would be minimized if you physically remove them or you put a Faraday cage around one of them. And so if you're still getting issues, it's probably in the hardware somehow. Like if it's a multiplexer or it's a multi-channel, something about how the signals are getting out are interfering with each other. I can't speak much more specifically. I don't know exactly what equipment you're using or how the electronics might be cross-talking or something strange like that. Yeah, the complete elimination, further away it is from the cell cycling, so there's some kind of crosstalk happening. The your ability to calculate um, the uncompensated resistance or the ohmic resistance, whatever, should still be low measurement. Like typically the behavior that you'll see is you'll have that sort of inductive tail at the high frequencies, and then it crosses the x-axis, and then you have your semicircles or whatever you have. You can still get that x-intercept point, right? I mean, I guess if you still can get that point, in theory, you should still be able to get your ohmic resistance measurement. It's just you have inductance in the way, and inductance is the inductance is something that is just so common and almost impossible to really get rid of, especially on systems like batteries that have really high capacitance and low impedance. And the inductance is sometimes thought of. I've seen it described as you don't get X intercepts because actually I don't know how that's possible. Is the entire impedance spectra underneath the x-axis? Like you don't have any behavior at all? That's a severe. If that's the case, you're either not going to a low enough frequency or you have such a severe amount of inductance that your problem is really, really bad. And that probably, because sometimes what you have is you have a tail, right? And with batteries or things like that, it tends to be either from the cabling, or also some people will say things like it's a uh, secondary storage kind of a thing. I've seen that explanation. I'm not exactly sure how or why, but it's on top of the x-axis. So if you don't get, it's on top of the x-axis, that's not inductance. Inductance requires positive phase angle, which anyway, I think I'm gonna have to look at your data, but I think that the yeah, maybe drift. It definitely sounds like you have some really severe cabling or shielding problems. Um, you're going to want to try to get shielded cables. You're going to want to try to keep. You might need to do something as severe as like get Faraday cages for each one of your setups, which is like literally like if you have 5, like this is your box and you have 5 leads coming, right? So you have like cell 1, cell pouch, cell 2, whatever. Get like, I mean, it would be like a shoebox, and like lined with metal, like aluminum foil or something like that, and cover, cover, cover each of them, like to the point that they emerge from the chassis, all the way. That if you don't have shielded cables, like really whatever good shielded cables, get like Faraday cages, not just for the pouch cell out here, but like the whole leads. You can try twisting them like I said, twist the drive and sense line separately. Ferrite beads. These are some other good options here. Consider a compensation circuit with a tuned capacitor. I mean, this is pretty extreme. You could. That requires a lot of trial and error. I don't know about ferrite beads. That might be good. I haven't done that before. But Faraday cages can help reduce the noise or crosstalk. It should keep electrical signals from interfering between each other. If it's an internal thing to the chassis, to the instrument itself, it's probably nothing you can do other than call the manufacturer and see if there's something they can help you with. If there's some setting, if there's a filter setting, something like that might help. But Faraday cages might be an answer for you. Give that a try. Because a little bit of inductance probably is always going to be the case. You're probably never going to get rid of it entirely, but it shouldn't be this severe. That does sound pretty bad. So, okay, Rajat has said, I have accidentally sonicated my glassy carbon electrode to clean it, but since then it is not showing the characteristic peaks of the ferrocyanide redox. How to fix it? Pretty difference between okay. So I guess I don't know, accidentally sonicate. So first of all, if it's like a rotating disc electrode or an electrode with a shroud, you can sonicate to clean these electrodes, but you only want to sonicate the tip. So I wonder if it's possible if you accidentally dumped the whole thing into like a beaker with water or acetone, like if the electrode itself, for instance, let me pull one up here real quick, just kind of talk through what I mean. Just getting. Okay, so let me share just to illustrate what I'm talking about. So, for example, this like something like this, right? So, if this is your glassy carbon electrode right here, and you put this, just the tip of this into a sonicator, fine. But if you put the whole thing in, this back part right here, right? This is metal. Like if this gets wet, you might damage the electrode, and that would be a problem for sure. So, that's the first thing. Now, if it's just a disc like this, the whole thing should be able to be sonicated. So I would be very surprised if just this part was sonicated and now you're having a problem. Something else is probably going on. It should be dried before it's put back into the electrode and everything like that. But generally speaking, electrode was shroud. It was dumped the whole, but only the tip was in water. So, okay, so basically you're saying you put it in, but just the tip part was in water, the backside was not. So it should not be necessarily a problem to sonicate. You might be concluding the sonication damaged something, and that may not exactly be the case. Maybe it is. I don't know. If your electrode was like loose, if the glassy carbon was somehow loose in the shroud, maybe sonicating loosened it worse. That's possible, I suppose. But sonication is generally a perfectly reasonable procedure to do over a short period of time to just clean and refresh the surface. So you might just have to try really aggressively repolishing your electrode surface. You might just have to do a long, like an hour of polishing, or something like that, to try to refresh it. The worst case is you would have to like send it back to a factory for factory repolishing, or you can do a really aggressive polishing, like take sandpaper and really polish it down, and then you'll have to polish with the alumina for, I mean, hours. It's very it's very frustrating, I'll be honest, but it's sometimes required. So yeah, so I would give that a try, and you might just have to keep on polishing it, testing it, and then polishing it again, you know, basically until it's operating properly. So okay, so sorry, I was just checking. Okay, the next, it looks like just making sure we finished wide arrow. So FCBS, the difference between RHE, SHE, NHE. So RH, the short answer is that they are basically all the same in most practical situations. A lot of people use them interchangeably. Sonicator. Let me see here. Dropcast to take DPV. Yeah, I can talk about dropcasting in a moment. So let's see. So they're basically the same. I'm just trying to make sure I say which one's the right one. So NHE is the normal hydrogen electrode. SHE is standard hydrogen. The SHE is at standard conditions. So like one atmosphere or 1 bar, one molar, I guess, like 1 molar like sulfuric acid, standard conditions. NHE is or what is it? SHE is 1 bar, NHE is 1 atmosphere, and RHE is the one that's pH dependent. Is that right? Something like that. Basically, for all intents and purposes, they are the same. They're used almost interchangeably because most of the time we're referring to the same thing, which is just the standard, the standard system, which is, and whether you're doing 1 atmosphere or 1 bar, the difference is very minimal. At most you're talking like microvolts, if there was any difference between the two in terms of which conditions. But RHE is relative. Was it relative hydrogen? Reversible hydrogen. And I think the RHE is the device itself, like where you can change the concentration of acid to change the potential a little bit. But honestly, for the most part, I mean, practically speaking, most people just in a paper, for example, use SHE or NHE, and they use them relatively interchangeably. But one of them refers to the standard conditions of 1 molar or 1 normal or whatever, and 1 atmosphere or 1 bar. Yeah, I almost never think about them separately, to be honest, and they're almost never used separately. They're almost used pretty much interchangeably. So yeah, so I wouldn't, I guess that's what I would say about that. There's a lot of back and forth here about the inductance, and let me see here if I missed anything. Faraday cages. Yes. Get the ferrocyanide. Okay, yeah. So, okay, looks like this might be the last question I'll get to. How do I drop cast properly to take DPV? So whether you're taking DPV or anything, I suppose, drop casting, I can describe the process for you, and then that will be it for this live stream, I suppose. So it's either a 1 or 2 step process, usually, and it involves ink prepared with the material you're trying to study, right? Whether you're doing DPV or CV or bulk electrolysis or anything like that. And so typically you prepare a small vial or beaker or small vessel, right? With either water or alcohol or a mixture of both. And the material that you're studying, whatever the usually a nanoparticle or powder of some kind, and you mix it up and make it well mixed, well dissolved, whatever you're doing. Okay. Sometimes you do that by stirring, sometimes by sonication, whatever it takes to get the material well dissolved, well dispersed in your ink. Then you're going to take your electrode, your usually glassy carbon, which is what you're talking about here when you're having issues with the surface. In any case, the electrode will be facing upside down, and you're going to take about usually 5 to 20 microliters in a micropipetter and drop it onto the surface. If you can spin the electrode, it helps it dry. If not, you just let it dry naturally. Sometimes you can put like a vent tube near it and dry the solvent, and then that causes the catalyst to dry onto the surface. You want to make sure that the droplet and the catalyst is entirely confined to the glassy carbon disc and not spreading onto the shroud, because if it spreads onto the shroud, you don't know how much is on the shroud and how much is elsewhere, right? So there's that. The second step is to put some kind of ionomer on top. Usually people use a Nafion dispersion, diluted 100x. So usually what they sell is like this 5 weight% Nafion suspension. So you dilute it 100 times, so it's a 0.05 weight%. You take the same amount of droplet, like 5 to 20 microliters, and you drop that on top of your disc and let that dry. That acts like the glue. So it's keeps your film on the surface, because otherwise it's just kind of fizzy-sorbed and it might not stick. And so you need that kind of ionomer as a glue, basically. The way people sometimes do it is they mix that Nafion in the first ink that I described. And so you just have one droplet. And so you have the droplet that has your film plus ionomer, glue, everything in one step. People do both. So you can try both of those. But basically, that's roughly how you make a thin film onto a surface. There's a lot of variation there. There's of course a lot of trial and error. It's really more art than science, to be honest. But hopefully I kind of described it very generally for you there. Okay. So all right, I am going to call the live stream there. I think I hopefully answered everybody's question. If I didn't, my apologies. And please, again, you can leave a comment on the video, and I'll get to it when I'm able to. Thank you for everybody who's joined me this week. I do appreciate it. Hopefully next week, I think I should be around. I don't know if Alex is around. He might be a few weeks out. He's got some travel now. And hopefully by September or October, we'll be back with you on a semi-regular basis. Until then, everybody, I hope you all have a good weekend. And if everybody's starting their semester soon, it's about that time, right? It's August, so soon classes will be starting up again. Everybody will be busy. In any case, I will catch all of you later. Have a good weekend and take care.